University of Bristol, and well, I'm going to talk to you about random packing of mixture of hard rods and spheres. So I'm going to start first with an introduction, and I'm going to try to explain you why I'm doing what I'm doing, and then I'm going to talk about 3 different methods that I use to this, and then I'm going to finally talk to you about mixtures of spheres and sphere cylinders. So, well, as you know, with hard body interaction of rod-like particles, we can get liquid crystal phases, and when you increase, So when you increase the aspect ratio of these sphere cylinders in this case, so these phases appears at lower density when you increase the aspect ratio of these sphere cylinders. So we can use this to explain or to understand why in colloidal suspension, in colloidal liquid crystals, we can get this behavior with low density. So, well, I'm going to explain you a little bit about colloidal liquid crystals. So in these things, in these colloidal suspensions, we have, so what we have is particles that are sterically stabilized, and you can have these with different kinds of particles. What we do in our group is we use clays, and one of the clays that we use are rod-like particles. So you stabilize them and you put them in a solvent. In our case, we use toluene, and you make your suspension at, depending on the concentration, is this phase separation that you're going to get. So in this case, we have here the nematic phase, and this is the isotropic phase. So this is a picture of a suspension put in a cell and seen between cross-polarized. So that's why you see these bright things, that is the nematic phase. And well, here there is a picture of a TEM picture of the rod-like particles. So you see they are thin and really long. In this inner case, we work with aspect ratios of like around 30. So when you compare this, when you compare our phase or boundaries for the transition between the isotropic and the nematic phase with what was reported by Bolhois and Frankel in a work that I think some of you will know, we found that we have these are all data, these black points, and we found that we have the isotropic boundary at a lower density. Well, this is a rescale density, and the nematic boundary at a higher density. But what happened is that when we do these suspensions, we fractionate them. So we have a lot of particles suspended on the solvent, and when we fractionate them, because they don't have the same length, so we fractionate them, but we don't always get the same length for all the particles. So what we have is that we have a high polydispersity of around 40%, and that makes our system not behaving the way that we expected. So, well, another thing that we do with this, with these things is that we have been mixing them with the spheres. And, well, this that is here is pictures of rods, mixtures of rods and spheres. And in this case, the rods are dyed up, and that is what you can see here, the rods. But depending on the concentration of the mixture, you can get funny things like this. That is a network where we think that what we have is the rods in a nematic phase surrounded by the spheres. But as I told you, these systems, depending on the concentration, they behave in a funny way, So what we want to do is we want to see how these phases behave depending on the concentrations of the rods and the spheres, and we want to try to find where these different phases are. But what we have in reality is that our system behaves funny because we have different things happen. So, for example, the polydispersity, but also not all the time we can get rid of all the interactions. So we ended with some bundles, and we think that another way to compare this or to study this is doing random packing. So that is why I'm doing that. So what is random close packing? Well, basically, it is the highest packing fraction that you can get in an isotropic system. Well, it's to some degree an isotropic system. So there are two main ways of doing this. We can use sequential generation models, or we can use collective arrangement models. In the first one, what you have is a box where you keep adding particles until you are not able to do it anymore. And in the second one, you start with a box with particles and you start compressing it and moving all the particles until you are not able to do it. So in the first one, what you get normally is a loose packing fraction. And in the second one is, well, when you are able to get a highest packing fraction. And well, there are different models to do this. There's not a fixed way, and there's not also a fixed packing fraction for all the aspect rate. Well, there is not a fixed packing fraction for all this system. So we start playing with these things, and we do something similar or something inspiring in a Monte Carlo. So what we did is what we call Monte Carlo-like compression. So in all these things, we always start with an isotropic system in a dilute configuration. So we have our initial configuration. In this case, we compress the system. And if we find an overlap, what we do is we go back to the previous configuration. We move the particles, and then we move all the particles, and then we compress again. And if in the first part we don't have any overlap, we just do this anyway, and then keep compressing and doing it until it's not possible anymore. So what we have here is a graph of my data obtained with this, and I'm comparing it with a previous model that I'm going to explain shortly. But what you see here, I'm just putting the nematic region and the isotropic nematic transition found by Bolhuis and Frenkel, just to compare. My system is not in equilibrium, and I'm not expecting any of these phases. But I want to compare, because we are interested in high aspect ratios, I want to compare this. So as you see, what happened in this system is when you are between the aspect ratio between 0 and 3, what you have is a high packing fraction, higher than the one for spheres, and most of these systems behave like this. It doesn't really matter which method you use, you always get this kind of peak. And well, what we want to know is if our system is isotropic. So well, there are some pictures of my simulation with different aspect ratios. But and for all these simulations, we always calculate the nematic order parameter. But well, this doesn't tell us a lot. So what we did, because the nematic order parameter is always between, for these systems, between 0.01 and 0.04. But what we did was also to calculate the G2 function, the pair distribution function, and this tells us a little bit about the order of the system. And as you see, we have something like some bundles, so that indicates some kind of order. So what we did next is we did the other method that I told you about. So how this works? In this case, we consider a system. We consider that each particle is moving away from its overlapping particles with a certain speed, and with that we calculate the translational velocity and the rotational velocity. And in this, we move the particles in this direction, move and rotate. So how it works is like for each overlap, we calculate for each pair of particles, we calculate the overlap. We calculate the direction in which we need to rotate and translate them, and we do it. So again, how it works is we have our initial configuration, we compare the system, but in this case, when we found these overlapping particles, we do these calculations, and we only move these particles. And we keep doing this until it's not possible. But what happens at high packing fraction, when you're just getting closer to your final packing fraction, is that you need to do a lot of movements. And this takes a lot of time, because each time you move one particle, you are creating new overlaps. So we did this for 3 different packing fractions, and then we decided to do our own approach. So we did kind of a hybrid model. So we used first the mechanical contraction method, and then we used the one that we used before, the Monte Carlo-like conversion. And what we got are these purple points. So in this case, our packing fraction are slightly lower, and this indicates also that we have less order. And well, there are some pictures of some of the packing fractions. And we calculate again this pair distribution function. And well, as you can see, this goes down earlier than before. So what we're really interested on is the mixtures of spheres and spherocylinders. And as I told you, we're interested in seeing how these packing fractions change and where and we are interested in drawing this here. I know this is we're not going to have any phase really, but we want to see how it looks here. So we start doing this with L/D equal to 5, and in our case the rods had the same, the diameter of the sphere was equal to the length of the rod of the spherocylinder. And well, we did this for 3 different configurations. In this case, we have 600 particles. This is 800 particles, and this is 1,000 particles. And in this case, we have a higher packing fraction than the packing fraction for rods, for spherocylinders, but we have a lower packing fraction than the packing fraction for only spheres. And if we see the system without the rods, there are the spheres, and there is a space. Well, maybe you can appreciate it in these pictures, but there are spaces between the spheres. So we have rods, spherocylinders in the middle. And well, what we want is to draw this like this. And as you see, this seems to behave in a linear way. This work is still in progress, and we want to do this for L/D equal to 20 and to 30, because this is what we are interested on. And well, this is what I have until now. Thanks to my supervisor, my group, and you for listening.
When people do the jamming of hard spheres, they find a structure factor that decays like 1/k.
Mm-hmm.
Do you get anything like that in your system? Not decay, sorry, a small k, it diverges like 1/k, I should have said.
Sorry, say it again.
For hard spheres, when you jam them and you're very near the maximum packing, the structure factor goes to infinity at k equals 0 as 1/k.
Yeah, I have that. Yeah.
So you have the same result.
For spheres.
And for rods? Something similar?
For the structure factor?
I just wondered if there was a special case for spheres or whether rods showed that behaviour too. It would manifest itself in some algebraic tail of these, of some radial distribution functions.
Well, the radial distribution function for aspect ratios like lower than 4 is, well, it behaves similar to the spheres one, but then it just goes like down. I don't know if that answers your question. Sorry.
Thanks again.